Hello and welcome. In this module we will look at propagation of electromagnetic wave or light inside phase modulator, and then we will also, if possible we have time, we will also look at propagation of wave in a amplitude modulator. That is to say, we consider the physical basis of phase modulator and amplitude modulator. Okay. We have seen that an electromagnetic wave, light is an electromagnetic wave, and this electric field or a magnetic field of the electromagnetic wave which is propagating along a particular direction. So, let us say propagating along the next polarized wave, which means its electric field will be oriented along the x direction, and it will have an amplitude of E0, and it will have a certain frequency omega, propagation constant k, z. Okay. So, this particular electric field corresponds to a propagating wave where the wave is propagating along x direction. I also know that if there was one more electric field, so this is x electric field, if I had one more electric field which is polarized along the y direction, then that electric field can also have a different amplitude. Assume that it will have the same frequency because we want to consider that scenario, and then it will have certain k and z, right. So, it will have a certain k vector or the propagation constant, and it will be propagating along z. These equations hold when the medium is linear, homogeneous and isotropic. Now, let us assume that the medium is linear and homogeneous, but let us now assume that the medium is anisotropic. Okay. If we assume that the medium is anisotropic, then what happens? The corresponding Ex component will see a propagation constant which is Kx, Ey will see a propagation constant which is Ky, and this Kx and Ky are not in general equal. Okay. So, this is the result of propagation through a anisotropic medium. So, we will not look at anisotropic medium for now, we will reserve this treatment of anisotropic medium later, but then what you can imagine is that if I take an anisotropic medium, I will not go into details, but I am trying to motivate the phase modulation to you. If I take an anisotropic medium of some length L, okay, and then I have a wave which has both Ex component as well as Ey component, okay, and it is propagating along the z axis. So, you have both Ex as well as Ey components, right, and then the wave is propagating along, this is the Ey component, this is the Ex component, the wave is propagating along the z direction. Okay. So, at z equal to 0, let us assume that both amplitudes Eox is equal to Eoy. Okay. So, this is Eox, this is equal to Eoy. Let us assume that at this stage both amplitudes are the same, they have the same frequency, they are propagating along the z axis. So, this is at z equal to 0, this is at z equal to L. Now, because this is an x polarized wave, it will see a propagation constant Kx, okay, and I know that the relationship between Kx, omega and Vp, correct. So, Kx is given by omega by Vp, phase velocity Vp is given by 1 by square root mu epsilon. Okay. This can be rewritten as c by square root epsilon r, where c is the speed of light in vacuum given by 1 by square root mu 0 epsilon 0, and epsilon r is the relative permittivity of the medium. Okay. This square root of epsilon r in optical literature, or in fact in literature, is actually denoted by n, standing for refractive index of the medium. From this relationship I can go back and write. So, I have k is equal to omega by c into n, right, and then go to kx and ky. So, k is equal to omega by c into n. This omega by c is a number that is determined by the frequency and speed of light in vacuum or in free space, right. So, that is denoted by k0. So, k in general is k0 into n, where n is the refractive index of the medium. Okay. Now, if the medium is anisotropic, then the refractive index n, or equivalently the permittivity epsilon, will be different for an x polarized wave and it will be different for a y polarized wave. So, if you are considering the x component, then this x component must see square root of epsilon rx, whereas the y component or the y polarized wave will see square root of epsilon ry. Equivalently, x polarized wave will see nx, y polarized wave will see ny. Okay. So, the corresponding propagation constants Kx will become, for the x and y polarized wave, they will become Kx is equal to k0 nx and ky will be equal to k0 ny. Is that okay? Now at z equal to L, these waves have now propagated a distance of L. So what will happen to the electric field EOX? Well, EOX or the x component electric field, it will propagate like this: EOX e to the power j omega t minus k0 nx, and what is the distance it has propagated? L. Why this L? Because you have an equation which says e power j omega t minus kz, where z would be the distance of the propagation, right. So z is at any point along the space. So here I am considering the plane which is z equal to L. So this would be e power j omega t minus k0 nx L, sorry, this j is for the whole thing. Similarly, the y field would also arrive. We had said that the amplitudes of these two are equal, so we can stick to that condition and call the common amplitude as A. So A stands for the common amplitude of the x field or the x wave, and for the y polarized wave you have the amplitude A and omega t is the same, but then its propagation term will be different because k vector will be different. L is the same, but k vector is k0 into ny for the y polarized wave. Is that okay? So this has to be written, sorry, with x and y hat, because I have vector quantities on the right hand side. So these are the x wave, x polarized wave and y polarized wave which are propagating here. Initially this total wave was a combination of x and y polarized wave, correct. Initially it was linearly polarized because x component wave was equal, y component amplitude was equal, they were both in phase with respect to each other because they were coming from a homogeneous linear isotropic medium. Now once they have entered an anisotropic medium and their refractive indices are different, right, because one is x polarized wave, the other one is y polarized wave, their refractive indexes are different, their propagation constants are different, and when they exit the anisotropic medium you will see that there is essentially a phase difference between the two, because the total electric field can be written as Ex plus Ey, which is x hat A e to the power j omega t minus k0 nx L plus y hat A e to the power j omega t minus k0 ny L. You can take this A e power j omega t as a common factor, and in fact you can take this A e power j omega t minus k0 nx L as a common factor, okay, and then what you are left here will be x hat plus y hat e to the power j, or rather minus j k0 ny minus nx into L. This term k0 ny minus nx into L will give rise to a phase shift between the two components, okay. So what you have seen is that there is a phase shift between the two component, and if for some way, if I can make this phase shift be a function of the external applied voltage, then I have obtained phase modulation, correct. This would actually become amplitude modulation because this phase modulation gets converted into amplitude change as well. If instead of having two components I take only one component, okay, I take only one component, that is say Ex term or the Ex x polarized wave which has an electric field component Ex. So if I take only this term, pass it through a medium, not an anisotropic medium this time, I mean the medium could be anisotropic, but you do not want just anisotropy in this case. You want to have a medium which will relate the phase shift to the applied voltage, okay. So let us say I have a certain medium which is, you know, this particular medium, I will call this direction as the z axis and call this as the electric field Ez. These are conductors, okay, these are conductors. I will maintain a certain voltage here. So I will maintain a certain voltage V of t, which is a function of time in this particular case. I know that for two conductors, if I maintain a voltage difference V, then I will generate an electric field inside, right. This electric field is directed along z axis, and the wave is now propagating, instead of z axis the wave is propagating along x axis. It has a certain initial amplitude, it has a certain amplitude initially, that is outside this particular region. So these electric field lines are directed from the top to the bottom, they are uniform, we are assuming that the plates are very wide area and they are placed very close to each other. So the electric field is uniform down there, okay. So this is E0, which is the amplitude at the outside of the region where the electric field Ez exists. Please note that this is a wave, optical wave. So, this is optical wave, whereas this black one which I have written is the electrical signal or the field that is generated by the electrical signal or the voltage V of t. Okay. So, just before this region is there, you can consider, you can write down what is the electric field for the wave, optical wave, that would be E0 e power j omega t, or we can write this as e power j omega st. This can be directed along some axis, but this is propagating along z axis. Okay. So, this optical wave is propagating along x axis. Okay. So, this plane is x equal to 0, this plane will be x equal to L. So, what will be the electric field at the output region? That is, as the optical wave propagates through, it is subjected to certain electric field. Okay. And what happens is that this electric field will change the refractive index of the medium. Okay. The refractive index of the medium before the application of the voltage V of t is N0, but after you have applied the voltage, the refractive index inside this region, that is between x equal to 0 to x equal to L, becomes N0 minus 1 by 2 N0 cube R33 Ez, where Ez is the electrical signal, okay, electrical due to V of t. So, there is this electric field which is generated because of the applied voltage V of t, okay, and that electric field Ez will affect this particular refractive index. Okay. Since E and V are related for a plane capacitor type of a situation that we have considered, Ez is given by V of t into d, where V of t is the slowly varying function of time which we have assumed. So, you can substitute for Ez and write this as V of t into d. What you have just observed is what is called as Pokel's effect. And what is Pokel's effect? Pokel's effect implies that you can apply external voltages. So, this is voltage or the potential difference, and then change the optical properties. That is, you can change the refractive index from N0 to some N0 minus half N0 cube R33 Ez, okay, Ez being the result of applying voltage V of t. So, Pokel's effect implies that you take voltage, which is the voltage that you can apply, and then change the optical refractive index. Okay. This change in the refractive index, which is half N0 cube R33 Ez, will be linear in electric field, correct. Initially the refractive index was N0, after you have applied it has become N0 minus half N0 cube R33 Ez, right. So, the change in the refractive index is given by delta n equals minus half N0 cube R33 Ez. This change is some constant times Ez. So, this is called as linear Pokel's effect. Okay. So, this is the linear Pokel's effect. So, what does this effect imply to us is that the electric field of the optical wave after propagating through this medium, when it comes out at x equal to L, will become E0, its amplitude has not changed, e power j omega st minus k0 n into L, correct. N is the refractive index, but I know that the refractive index n is given by N0 minus half whatever this expression, correct. So, I can rewrite this as E0 e power j omega st minus k0 n0 L plus half k0 N0 cube R33 V of t d into L, where d is the separation between these two plates. Okay. So, this particular element on which we have deposited two metal electrodes and applying a voltage V of t between them, causing the change in the refractive index, is coming from lithium niobate. Okay. So, this material is lithium niobate. In fact, this is a crystal. It will not look exactly like this, it will actually be in the waveguide formulation. So, you have to actually make an optical waveguide such that you have a substrate. Okay. So, you can imagine that this is the substrate that I have, and on this substrate I put two metal plates, okay, and then put a voltage between the two. The light will enter from here, this particular region. So, the light will enter in this region, the electric field because of the voltage that we have applied is going through in this way, and then as the wave propagates, this is x equal to 0, and as the wave propagates and comes out at x equal to L, its phase has changed, okay. And this phase change would have been just k0 n0 L if the electric field was not applied, but because we have applied an electric field or we have applied a voltage difference, the phase will be different, and in fact the phase is actually a function of time now, right. The phase is now a function of time. This is very crucial. If V of t is equal to 0, this corresponds to having applied no voltage and hence no electric field. So, this term would be vanishing. So, there is just a constant phase shift, there is nothing you can do, just happily go home without constructing a phase modulator. But now you have a situation where your phase is varying with time because you have applied a time varying voltage V of t and managed to introduce a phase shift into the optical wave itself. By applying a voltage V of t, you generate an electric field. This electric field will influence the refractive index, and that refractive index change when the optical wave observes it will lead to a phase difference, okay, or a phase shift which is now changing with time. So, I will remove this constant phase term, not very important for us, and I will simplify this remaining part, okay. So, I will write this one as V of t divided by V pi, okay. So, I will write this as V of, or rather I will write this as pi V of t by V pi, and then I will leave this as a simple exercise for you to find out that this V pi is given as lambda divided by n0 cube r33 L, or rather d by L. L is the length of the phase modulator, d is the distance between the electrodes that we have taken. Lambda 0, actually lambda 0 is the free space wavelength. Free space wavelength is given by C by f0 or f, whatever the frequency that we have applied. So, our frequency was fs, and R33 is called as the electro-optic coefficient. This is called as electro-optic coefficient, okay. So, this V pi is called as the half wave voltage because your output, which is now written as e power j omega st plus pi V of t by V pi, right. This is now a phase modulated wave, correct. So, this is a phase modulated wave, right, and when V of t is equal to V pi, the total phase shift will be equal to pi. So, that is why this V pi is called as half wave voltage. V pi is called as half wave voltage. You might wonder why there is this half wave. Half wave simply means lambda by 2, and we know that lambda by 2 corresponds to a phase shift of pi, because lambda corresponds to a phase shift of 2 pi, lambda by 2 corresponds to a phase shift of pi. So, this is called as half wave voltage. Let us do a simple example here, okay, to calculate some numbers. So, let us assume that the thickness d is about 10 micron, and let us say the length of the modulator is 5 centimeter. Let us say in the absence of any input voltage, n0 is 2.2, the Pocal coefficient R33, which is the electro-optic coefficient or the Pocal cell coefficient, is given by 30 picometer per voltage. That is, if you apply 1 volt, you will get R33 of 30 picometer, okay. You can calculate what is the half wave voltage for this, that is, you can calculate what is V pi for this one. Substituting the values, so I have to give you what is lambda. So, let us say lambda is 30 nanometers, okay. Substituting this into the expression, what you will find is that V pi is given by around roughly about 0.94 volts, okay. So, calculate this by writing the formula lambda 0 by n0 cube r33 d by L, right, okay. So, you can use this equation and then you can find out that V pi is very small. In fact, this is the magic of integrated optics. You can buy a lithium niobate crystal separately, which will be of this particular bulk region, and this size crystal or smaller crystal, and then put some electrodes on the top and the bottom, apply a voltage externally, okay. But because this this d, the thickness is very large, right. So, the V pi voltage will also be very large because it would be directly proportional to d. So, V pi is very large for a crystal that you can purchase and then deposit certain electrodes and then apply a voltage. When in an integrated form, the separation between the two electrodes is drastically reduced. It is just about 10 to 50 micron, and then the length is around 5 to 10 centimeters, and then your V pi is very manageable. So, you get in market phase modulators with a V pi of about 3 to 4 volt peak RF signal, okay, or 3 to 4 volt voltages. So, V pi is just about 3 or 4 volts, which is very, very small compared to about 100 volt V pi that you will normally get with a crystal operating alone, okay. So, what we have seen is that it is possible to talk about the phase modulator by having a electro optic crystal, okay, and then putting them in the integrated optical framework. One last point, this crystal is usually, as I said, lithium niobate crystal, and the way which we have indicated here is that the lithium niobate crystal is cut along the y axis, okay. It is cut along the y axis, the wave is propagating along the x axis, and the electric field is indicated along the z axis. This is called as a Y cut lithium niobate. It is the most important configuration for lithium niobate optical phase modulators. In fact, all optical modulators are made out of lithium niobates. Commercial optical modulators which are operating for optical communications are made out of lithium niobate modulators. They are all usually Y cut, and you have X propagating wave. But please remember, what is Y cut, what is X cut, and what is Z cut is the crystal frame of reference, not our frame of reference, okay. So, one has to perform some crystallographic studies in order to locate the principal planes and then cut your crystal along that particular plane. So, this is the Y principal plane that you will have to locate and then cut along that particular plane of the crystal. So, what we have seen is that if you just take such a lithium niobate crystal and apply a voltage, you will be able to induce a phase shift, and if the voltage is that you have applied is varying with time, you have actually managed to obtain phase modulation, right. Now, there is also amplitude modulation, correct. How do I obtain amplitude modulation? Well, we have already seen this amplitude modulation structure. So, you take a waveguide and then split this waveguide into two portions, right, and then you put two electrodes here, right. Each of these arms by themselves are phase modulators, right. So, you can apply a voltage V1 of t, you can apply a voltage V2 of t to this one, and then combine them into one waveguide. I should have combined them into waveguide type. So, each of them can be combined into a waveguide. Now, if you supply a wave, optical wave whose electric field is E in of t, you get an optical wave at the output whose electric field is E out of t. You have applied V1 of t, so you cause a certain phase shift phi 1 in the upper arm, you apply V2 of t, you cause a certain phase shift phi 2 in the lower arm, and then you combine the light intensity over here, right. So, when you do that, I am not going to derive this, but you should be able to derive it as an exercise, because you know how this can be modeled as a splitter. Assume a 50-50 splitter, you know how to obtain the electric field here, because this is simply phase modulated wave, this is one more phase modulated wave, and then you know how to combine them, right. So, when you do all that, you will see that E out of t will have components which is e power j pi V1 of t by V pi plus e to the power j pi V2 of t by V pi, okay. There will also be e power j omega st term, there will be some additional amplitudes here that I do not want to really worry about it, okay. So, there will be some additional factors constant that we can eliminate. Now, what we normally do is we eliminate this e power j pi V1 of t by V pi, that is we take this as common and end up here as e power j pi V2 minus V1 divided by V pi, okay. Then we also take this V2 minus V1 pi outside, so that I have e power j pi V1 of t by V pi, then there is also e power j pi by 2 V pi V2 of t minus V1 of t, okay. This is all common, and inside what you get is, or what you will get is cos pi V2 of t minus V1 of t divided by V pi. Okay. So, you can see that by changing the operating point, by choosing this V2 minus V1 difference, I can choose or I can make into different biasing points for the operation of the amplitude modulator operation. We have seen that when the bias is such that V pi by 2, when we bias at V pi by 2, you will end up having amplitude modulation, correct, because you know we have seen this earlier, the output amplitude E out will be equal to input amplitude E in of t times sine of whatever the message signal that you are transmitting times pi by V pi. Okay. And for small values of m of t, this is very nearly E in of t m of t pi by V pi. Okay. So, this amplitude is getting modulated to E in of t. So, this is basically a amplitude modulated wave. Okay. You can bias this one at a different region. So, this is say you can bias it at V pi, and in that case your output power will be very nearly equal to m square of t. This corresponds to what is called as double sideband suppressed carrier modulation. So, these things I will give as an exercise because it is simply coming up with together, but one thing I would like to talk about before we close the module is this expression, right. So, if you look at this expression, what you see is that you can forget that this is a common factor, but then you will see that there is this particular term, right. This term which gives you an overall phase shift, right, you have to combine both terms, you will get e to the power j pi V1 of t plus V2 of t divided by 2 V pi. Okay. This term, which is sum of the two signals pi divided by 2 V pi, can lead to what is called as chirping, because V is changing, the incoming modulating signal which is say E0 e power j omega st, sorry, incoming carrier e power j omega st will pick up this additional phase, and if V1 of t and V2 of t are changing with time, then the overall phase will change with time. The overall phase, in addition to this amplitude, there will be a phase modulation. So, this change in the phase or phase modulation which is unwanted is called as chirping in the modulator. Okay. To avoid chirping, you have to operate the modulator in its push pull configuration, that is you have to operate dV1 by t by dt is equal to minus dV2 of t by dt, or V1 of t is equal to V2 of t minus V2 of t plus some bias voltage. So, this is where the bias voltage and the different operating conditions come in. Okay. This is called as push pull configuration. So, this is what I wanted to talk about optical modulator structures. We have talked about phase and amplitude modulator structures. Thank you.